I'm very pleased to be with you in this beautiful room and talk to you about the women who worked at the Harvard Observatory in the late 19th and early 20th century. So this is the way the building looked. And you can see there are two telescope domes, a big one and a small one. And then there's another part of the building where the astronomer lived. So the director was always there. And that made it easy for him to have his wife involved in the work, his sister, his daughter. And these were the first women who worked at the observatory, were the family members of the director. And because they did their work so well, the next step was to bring in women from outside and teach them how to do the necessary work. And this is what attracted me to the story, that a place like Harvard, which was all male and very uninterested in having women at the college, somehow the observatory became a place that was full of women doing interesting, important work. Edward Pickering came in as the youngest director to take over. He was only 30 in the 1870s when he arrived, and he wasn't really an astronomer. He was a physicist, and he was very interested in photography. And he had an idea to create a huge project in photography, which he did. Because by having a long exposure photograph, stars would appear that had never been seen by the human eye, because the eye doesn't accumulate light over time the way a photographic film can. So he was able to demonstrate how many more stars there were than anyone imagined. And part of the work of the observatory was to make a catalog of all the stars, so people at different observatories could compare information about them. And I love this photograph of the Orion constellation because it reminds me of this picture from Galileo's Starry Messenger. And it's the same idea. So when Galileo looked at that constellation through a telescope, he saw stars that had never been seen before, and he drew them into his illustration of that constellation. So these photographs were taken on glass plates, and most of them were negatives like this. So the stars appear as black dots on a white background, or the spirals show up black. And the presence of the photographs made it possible to do astronomy in the daytime, in the rain, and without looking through a telescope. So most of the women who worked on these plates were not telescope observers. They had this new way of studying the heavens. This was also a time when spectroscopy, the science of investigating light in all its wavelengths, was gaining popularity. And some of the photographs are of the spectra of the stars, not just dots, but the star's light spread out to spectra because people were interested in what elements occurred in the stars, which you could tell that way, and they were also interested in the motions of the stars, whether they were moving away or toward us. And they could tell that from the way the spectral lines were shifted. Of course, there was no color photography, so the very best of the stellar spectrum images looked like this. The reason that it says Henry Draper Memorial, so Henry Draper had planned to do this work, but he caught pneumonia and died rather young, and his wife wanted to see the work completed, so she lent her fortune to Harvard to pay the salaries of the women and pay for materials for this project. So this is what a lot of the spectrum photographs looked like. So each little smudge on this image is the spectrum of a star. And the black circle is just a coin. It's a 1 penny coin for scale. And you can see there's writing on the plate, there are numbers. So when the astronomers looked at the glass plates, they could write on them in colored ink on the side that did not have the photographic emulsion. And then they would be able to refer to each one by a number. And Pickering's idea was, give these images to the women and have them try to discern a pattern in the spectra to create groups of stars, see which ones had similar spectra, in the hope of making a classification system, just as there's a classification system for animals and plants. That was the hope, that they could do that for the stars. And this was the first woman who attempted that. She was a Scottish immigrant, and she actually started work at the observatory as a maid in the residence. But the Pickerings recognized how intelligent she was, and they moved her into the observatory and taught her how to analyze the plates. She was pregnant at the time, and her husband had left her. So she really wanted to go back to Scotland to her family to have this baby. And the Pickerings helped her do that and promised that she would have a job if she came back. So she did. And she made the first classification system of 10,000 stars. And she gave each classification type a letter of the alphabet. The glass plates accumulated in volume because people were taking these pictures all night long, every night, with several telescopes. So soon, you can see the observatory building with the dome in the background, but soon they had to build an entire new building just to house the glass plates. And they called it the brick building because it was made of brick, because they wanted it to be fireproof, because this was a unique resource. They recognized at the time the value of this record of what the night sky looked like every hour during the night. And they projected maybe they could do this over 100 years. They needed another building eventually. So at first, the women who were hired were just bright, young high school graduates. Some of them had worked as secretaries or record keepers for insurance companies. But soon they started bringing in the graduates of the new women's colleges. And the first of those was Antonia Mori, who was also a niece of Henry Draper. And the very stern-looking woman in the other photograph is Maria Mitchell, who was the first really famous American woman astronomer. And she got famous for discovering a comet. And she taught at Vassar College, where Antonia Mori was a student. So she became very well educated in astronomy. So here you have the working group. Mrs. Fleming is standing in the middle. She's not only come back, she's now the supervisor of the whole project. And you can see how they worked in pairs. So in the front, there's a frame. The plate is mounted in the wooden frame. And then there's a mirror at the bottom. So it's daytime. The windows are open. Light comes in, hits the mirror, and shines up through the plate. And so they have very good illumination, because you saw how tiny the spectra or the stars are. And they use a magnifying glass. Or the woman at the back is looking at a modified microscope. She's also examining a glass plate. Here's Pickering at the back, not really doing much, but he's definitely in charge. And just in front of him is Antonia Mori. So the person looking at the plate says out loud a number, maybe designates a spectrum type or whatever information, and then the partner writes it in a logbook. Annie Jump Cannon came from another women's college, and she really had a lot of experience as an observer, a telescope observer. So she was the first of the women at Harvard who did both. She looked at plates, she looked for variable stars, she also observed them through the telescope, and she took Mrs. Fleming's system and Miss Mori's changes to that system and created her own, which is still in use today. So those of you who have studied astronomy, you know we talk about O stars and G stars, and all of that came from this work. And what Miss Cannon did was to break the alphabetical order. And the stars are now really in order of their temperature. This is one of the spectrum plates that Miss Cannon looked at. So you can see she's written numbers in various colors, and she could look at one of these smudges and just almost instantly be able to put it in a category. She was also a diarist, which was wonderfully helpful to me to be able to go through some of her diaries and notice what she wrote the day she voted for the first time. They definitely lived through interesting times. And so to really make these plates a record of the entire universe, there had to be an observatory in the southern hemisphere. And so a group went to South America and found what seemed like an ideal spot near the town of Arequipa, Peru. And it was in the lee of a volcano, but the volcano was extinct, or so they believed, yeah. So only one building here looks like a telescope dome, but several of the others have a roof that slides off, and there are several working telescopes at the site. And this telescope is inside the dome. This was called the Bruce telescope because another very wealthy woman who had really no ties to the observatory was so interested in the work that she donated the $50,000 to build this telescope. So I think Pickering must have been very charming as a fundraiser, very, very effective. And the plates from South America were also shipped back to Cambridge to be analyzed by the team at Harvard. So Henrietta Leavitt, who we are celebrating with this exciting exhibit and the cycle of lectures, hers was the first name I heard of these women. And it was mentioned by astronomer Wendy Friedman, whom I got to interview when she was in charge of a key project on the Hubble telescope. And she was explaining to me that they were still using a method of distance determination that had been pioneered by a woman who lived in the previous century, and that was Henrietta Leavitt. So when I went to learn more about Henrietta Leavitt, and I found out she was working in a whole room full of women, that made it even more interesting. So Ms. Leavitt was not looking at spectra. She was trying to make a good system for determining the brightness of the stars. And she used these instruments. These were called fly spankers. So not a fly swatter, because that would kill a fly. But these were small, so they would just spank the fly. And they were made from pieces of the glass plates with stars on them that had already been judged to be of a certain brightness or magnitude. And then you could move this over another plate and make comparisons, and then assign a brightness to each of the stars on that other plate. And to follow the course of a variable star, you would have to look at many, many plates of the same region many, many times. It was extremely intense work, tremendous concentration required. Records were kept, of course. All of these logbooks are still at the observatory. Many of them have been digitized. You can look at them online. So this is Miss Leavitt's logbook of her observations of variable stars in the Small Magellanic Cloud, where she discovered nearly 1,000 new variable stars. These are her very neat records. Sometimes they took a photograph of a plate and pasted a piece of it right in the logbook to illustrate what they're talking about at that moment. So this is the object, the Small Magellanic Cloud, and now we know it's a satellite galaxy of the Milky Way. But at the time, People just thought it was a close cluster of stars. And as she looked at these stars and discovered so many variable stars, it struck her that just about everything in this group was about the same distance from the Earth. So those stars that looked brighter really were brighter. I mean, normally if you look at the sky and something is very bright, you can't tell if it's bright because it is bright or because it's very close by. But she felt these were all the same distance, so she could make meaningful comparisons. And she measured the periods of each of these variables, the time it took them to cycle through their changes. And she noticed that the brighter stars took a longer time. And she thought that might be significant. So she made a note of it. And then she really studied it, first in a group of 16 stars. And it really held up. And it was important enough for Pickering to publish, with credit to her, what an interesting thing she had noticed. And then she studied 9 more, and this relationship really held. So she published her findings with what has come to be known as the period luminosity relation, or the Leavitt law. And immediately other astronomers looked at those same types of variables in the nearby region of the Milky Way, and then used her idea to calculate the distance to the Small Magellanic Cloud. And it was really far away, much farther than anyone had imagined. So now there was a way to measure distances across space. People were very excited about this. In fact, both Miss Leavitt and Miss Cannon were world famous in their own lifetimes. Miss Cannon traveled a great deal. She went to international meetings of astronomers. She was given honorary degrees in the United States and abroad. And she even went to Arequipa and did some observing there. Miss Leavitt was never really very physically strong, and she didn't travel. She stayed at the observatory, and she had long periods of illness when she would sometimes go home to her family and convalesce, and Pickering would send her plates to work on. It's stunning to think of these very fragile glass plates just being shipped thousands of miles, but that's what they did. So Pickering's work with all these women attracted attention of yet other wealthy, interested people who created some funding support for women to come and study and learn at the observatory, but then be able to go work at some other observatory. And these were called Pickering Fellowships. And this picture shows some of the regular staff and some of the young women who became Pickering Fellows. After Pickering died, Harlow Shapley took over as director of the observatory. And he had visited the Harvard Observatory before he went to work on Mount Wilson. And he was inspired by some of the people at Harvard to study the globular clusters, which are these, that's the nice thing about astronomy is things have very descriptive names. It's a glob, it's a big glob of stars. And these were observed at Arequipa a great deal. People made an effort to actually count how many stars were in a globular cluster. You can imagine how difficult that would be. So these globs appear in many places in the sky. So Shapley had the idea to map them all, to use Miss Leavitt's idea and place all of these globular clusters in a schematic diagram. And this is how it looked. So the sun is at the intersection of the axes, and the red X is what he considers the center of the universe. So he thought this was very funny, that we think we're so important, and here we are, we're out on the edge of the action. We're nowhere near the center. And Shapley really wanted to create a graduate program in astronomy at the observatory. He felt they were doing a very good job of expanding the science of astronomy, but they weren't creating the next generation of astronomers, and he wanted to do that. But the only money he had to bring in students was the Pickering Fellowships for Women. So all of the early graduate students were women. So here, with her own little mappamundi, this is Adelaide Ames. To the right is Helen Sawyer, and at the bottom is Cecilia Payne, who came from Cambridge in England, thanks to these fellowships. And she actually got Henrietta Leavitt's old desk, and she used to like to work late at night, and so she would have a light on at her desk, and people walking by would say that it was the ghost of Miss Leavitt inhabiting the observatory. But she was the first person to work at the observatory who knew anything about atomic theory. And she was advised to look at the plates when she got to America and really try to figure out the abundance of the various elements in the stars. And she took that on. She had to create her own method. It was very difficult. She was frustrated for a long time. But eventually she did. And with Shapley's encouragement, she was doing this work as a dissertation for a doctoral degree. And she concluded that although most people thought that the proportions of elements in the stars would be just like they were on Earth, she said, no, actually, hydrogen is about 1 million times more prevalent than anything else. And this was really not believable. And one of the scientists who read her dissertation as an expert advisor said, you really better not say that too strongly because it's crazy. But that was her finding, so she reported it. She said it may well be wrong, but nevertheless, this is what the results of my work show. And it took only 4 years for everyone to come around and say, it really is mostly hydrogen. So she is the other great discovery being celebrated. This is her dissertation. Shapley decided to start a new line of publications from the observatory, and hers was #1 in that new series of monographs. He was terribly proud of her. But getting back to Miss Leavitt, so this is Edwin Hubble working at the Mount Wilson Observatory, and he was also using Miss Leavitt's stars to judge the distances of things. And Shapley had, when he measured the Milky Way, it was so enormous that he was convinced it was the entire universe, and that the spiral forms that people could see were just small entities within the Milky Way. But there was argument on both sides. So Hubble was looking at these spiral nebulae, especially the Andromeda nebula, and looking at it, taking photographs. There's a reason I'm skipping to Miss Payne. Well, in his photographs, he was realizing that Andromeda was so far away that it couldn't be part of the Milky Way. And he wrote this in a letter to Shapley before it was published, before the publication in 1925. And Shapley shared the letter with Miss Payne and said to her, "This is the letter that destroyed my universe." So this is Hubble's image. He was looking at a star at the upper, I don't know what it is for you, the upper left, which he thought was a nova. He originally wrote N next to it, but then as he watched it over time, it varied. So he wrote variable in red with an exclamation point. You know, people think scientists don't get emotional about things. This was a very exciting moment. And that was how he was able to judge its distance and show how very far away it was. Here's another image of the group. Miss Payne is the one seated at the drawing board. Miss Morey is in the front here. Miss Cannon is the one who's too busy to look up. And there's something about these pictures, you know, they're very dated, and there's something quaint about them. And I will admit to you that even though I chose the story because it was about women, the whole time I was writing this book, I kept being surprised by what the women had done. And this was very embarrassing for me because as a woman, I shouldn't have been so surprised. And it occurred to me that it was actually possible for a woman to be a misogynist. Because I think not really having high expectations of these women was a form of misogyny. And I very quickly discovered, to my horror, that I was not alone. One of the people I had asked to be an expert reader of my book was a professor of astronomy at Harvard. Her name is Alyssa Goodman. And when she was reading the manuscript, she said, "I have to apologize to you because I'm not really paying attention to your explanations of the science, of the astrophysics. I am just stunned by these women. Here, I've been at Harvard, I've heard all of these names, but somehow I just always thought it was a cute, quaint moment in our history. I never realized they were actually doing science." So she also had those negative feelings. And that's when I decided that from now on, I want to tell only women's stories. And that's what I've tried to do. And I really wasn't thinking of talking about Madame Curie because she's so famous already. But then I discovered that she had about 45 women who passed through her lab, and that was another story. A couple of things happened in my transmitting my talk, and I think I have lost the final slide, which is an image of the periodic table of the elements coded to show the origin of each element. So now we know that hydrogen and helium were formed in the Big Bang, and many others are formed in stars like our sun, and others in larger stars in cataclysmic explosions and collisions. And it's very interesting to have seen all of that come together from these discoveries. Thank you. And I'm happy.